On Friday, we're talking about the 3 different ways that we can deal with Faraday's Law. Now, the issue here is about getting these basics out of the way, because this is probably not what's going to be on the exam. They're probably going to try and encourage us to use this in a more creative way. So we have to kind of see the basics real quick. And Friday was, of course, dealing with the aftermath of our substitute issue. Let's see if we can't be a little bit more focused, or when I say we, I mean me, be a little bit more focused. And just as a brief review of Friday, I want to talk first about the idea that we would take a loop of some size and move it into a region with the magnetic field. I suggested we label this H, and I wanted to take a single snapshot, just a brief moment, where we could freeze everything at that instant and recognize that there is this much of the loop inside the magnetic field, perhaps an amount. I think I used Y here, so we have something as a placeholder. The first thing is recognizing that flux, although an integral, is really just trying to figure out how much magnetic field is passing through an area. It's a product. You're going to end this product with something that's going to be in Tesla meter squared. So you're going to be taking whatever area there is and multiplying by the size of the magnetic field. In the case of this one, I've got a rectangular section that is impingent upon the magnetic field. That rectangular section has an area of H times Y. That's how much magnetic field passes inside the loop. The magnetic field is bigger than that, but flux is all about the part that's inside the loop. This is an integral just to allow us to have situations where the magnetic field might be different at different places within the loop. I know you're not writing that down, but that's really the crux of why there's an integral there. To deal with situations where the magnetic field isn't the same everywhere. That's the most likely nuanced question that we will get. Bless you. A question where it's not the same everywhere, where you'll have to actually integrate. But we are more likely to be faced with situations where the magnetic field is the same everywhere. Now, I want you to understand something. It's easy to get this next part confused. Calculating the flux is different than calculating Faraday's law. Calculating the flux is looking at a single instant in time. I'd put that in your notes too, that we are freezing everything. We're not worrying about what's changing or how it's changing right now. In this calculation of flux, we freeze everything. So it doesn't have a velocity right now. At this instant, it is in the magnetic field a distance y. And that's all we know. We'll deal with how it's changing later. So this computation of the flux is almost always going to boil down to looking at these 3 variables: the magnetic field, the area, and the angle. When you do this, make sure you are aware that one or more of these could be changing. Okay, so in the case of this one, in all of them, you consider these 3 variables, and you have to be aware that it is situational, meaning if you know one of these variables is going to change, you need to likely pay attention to that part when you're calculating the flux so that you can have something to pass to the next part of the problem. For example, right now, I don't have anything to pass that much to the next part of the problem, except that in the next part of the problem, I know the magnetic field is going to be B. It's constant. It's not changing. I know the area is going to be the product of H and Y, because it's length times width. It's that straightforward. It's an area. And although it seems ridiculously silly right now, trust me, you'll make this mistake later. Students always do. And the last part is the part that people forget, cosine theta. But the cosine here has to take into account the direction of the magnetic field as compared to the area of your loop. Now, I need a brief reminder, I guess, that you recognize that the loop can either be, is an area, the loop is an area. And that we say the direction of the area is perpendicular to the surface. So in this case, my theta is going to be 0 or 180 degrees, just because of the way I drew it. But don't automatically throw that away. Be aware that if that's the variable that's going to be changing, you may want to put a placeholder there for later use. And trust me, that's going to be case number 2. This is case number 1. But I know that over time, in this example, the angle's staying the same. So I can put in the variable there that I know is going to be 0 degrees and just leave it that way. And not worry about the fact that it's changing, because over time, it's not changing. Remember, the calculation of the flux isn't about what's happening over time. The calculation of the flux is what's happening in that instant, but you're trying to be aware of what's happening over time. So when we're done, we have for our flux, in this case, BHY, and this is right where we left off at the end of the class period on Friday. So now we pass this to the second part of the problem, meaning that was enough to get us the start of the question. But Faraday's law isn't about the flux, it's about how the flux changes with respect to time. This is Faraday's law. Now, in computing Faraday's law, there are several factors that you need to take into account, but almost always the most important thing to consider is the derivative. And you won't be given what you think or things that you necessarily need. You have to see how the derivative applies in your particular case. For this one, we know that the value for n is 1. And generally, just be aware that n stands for the number of loops. They can slip that in, especially in multiple choice. You can probably imagine that. They won't say loops either. They will say turns. And I would probably emphasize that in your notes with maybe a box. That the general term used to describe n here isn't how many loops there are, but how many turns of wire there are. Now, continuing on, we'll be taking the derivative of whatever you calculated for flux. Now, it's at this moment where you recognize that your EMF is based largely on which of these variables is changing over time. And you'll notice we created a placeholder to use here purposely for this moment. Ask yourself, which of these variables is changing over time? Is the magnetic field changing over time? The answer is no, it passes through the derivative. Is the height of the wire changing over time? No, so it passes through the derivative, which leaves you with negative b times h times dy dt. Y is changing over time. It's getting bigger. Now, you should all be able to recognize that we're looking at the rate at which y increases. We probably have a variable for that. It's going to be the velocity. This is the rate a position is changing. Y represents the position of the loop with respect to the magnetic field. So that makes this BHV. We already knew that. We've done this before. Our first example was to look at motional EMF, and we came up with BLV as the answer already. So this isn't a surprise. It's important that you recognize I chose H here just so that we can see the similarities and the difference between this formulation of EMF and motional EMF. They're the same, but we get this negative sign here, and that's not accidental. The negative sign is a reminder that the direction of our EMF is purposeful in creating a current that is opposing the change. So in this example, you should be able to figure out the direction of the current that's created in this loop as the loop is pressed into the magnetic field. Remember, it's supposed to oppose the change. So if I'm trying to create a magnetic field that opposes the change, I am adding a magnetic field to the loop that is into the board. My current has to be created in such a way to make a magnetic field that opposes this introduction of a new magnetic field. So my current direction should create a magnetic field that's out of the board. That's what it should attempt to do. And that would have to be a current that's in this direction. That whole argument handles the negative sign there. Remember, the negative sign, although it is mathematically required here, it's about direction. Now, whether you have to include that negative sign for the rest of this, answer is typically no. That when they ask about the direction of the current, that'll be enough. And they will ask about the direction of the current every time. All right, so emotional EMF, this is case one. A current loop being dragged into a magnetic field. You should probably realize that it's the exact same kind of thing as a current loop is being dragged out of the magnetic field. The only difference is that the current direction changes as you drag it out of the magnetic field. All right, we've done this one a lot now, several different ways. Any questions about this one? All right. This came up and I think it was on Wednesday. Luke asked about it. Flux. As a calculation goes, B.dA yields Tesla meter squared. This is sometimes referred to as a Weber, as a unit, the Weber, Tesla meter squared. Now, you should take a moment. I'm not sure when you should do this, maybe in the next few minutes, because I'd love to pick on one of you to see if you can do it. This is not easy, because it's in your notes, but it's scattered through your notes over the last couple of weeks. EMF is the derivative of the flux, which means it's got to be Webers per second. Is this a volt? I think 120 seconds should be enough for you to tell me. So we're partway there. We got your kilogram meters per second squared. What I got in the denominator there? Ah, coulombs, good job. Meters per second, all right. This appears to reduce a little bit, wouldn't it? And can you help me with that part? All right, so that's a Tesla. Wait.
Yep, we're good.
You sure?
Yep.
That's the way math works, last time I checked. All right, now see if this gives us the appropriate units. Of course, we now have to consider the EMF portion of this, which we know should be in volts. I'm not sure if... I'm sorry. Is it time for something to happen? Now, to make sure that we do this right, I want to remind you, do you know what a volt is? Because if you don't know what a volt is, that's going to make this harder. But we're going to keep going, assuming you do know what a volt is. I'm not convinced. But a Tesla is a kilogram per coulomb second times meters squared all over seconds. Jake, you wanted to help before.
I did before.
I'm willing to let you help now.
Well, I mean, I just had it in my notes as Newton second per coulomb meter beforehand.
It would have been easier if we left it there.
Yeah.
But that ship has sailed already, so we have to keep going with this ship.
It's never too late.
So now it's just kilograms meters squared over coulombs, isn't it?
Close. Kilograms meter squared over coulomb second squared.
Gotcha.
Those seconds don't cancel out. They're both considered in the denominator. So we're close. It might not be a bad idea to remind us a little bit about what a volt is, which is a joule per coulomb. I bring it up because remember, volt is defined as work per unit charge. So a volt is a joule per coulomb. If I look here, can this be grouped in such a way as to produce the desired unit? What? I bet you did. All right.
You could take the kilograms meters second, make that a force, and then take the meter to get F times D work. So that gets you joules per coulomb.
You were very close, so I will kindly give you some of it. Just breaking it up a little bit. All of this is a Newton. So that would mean Newton meter per coulomb, which is joule per coulomb. So joule per coulomb or volt. Sure does. Sure does. That's a long way, but I wanted to make sure we saw that because Faraday's law is a little bizarre. The fact that it still works out to volt, kind of nice. All right, the next one is ridiculously simple, I guess. If we have to, we'll go a circular loop of wire, radius r. But in this particular circumstance, our magnetic field is a function of time. Okay. Some function of time. Now, I want to be very, very clear. If they're trying to get you on the exam, they can give you any function of time they want here. Anything with a t in it will be fine. I'm saying that because your function of time could be something like a t cubed plus b t to the negative 1. Who knows? A couple of coefficients and a couple of t's. It could even be more complicated than that. We've seen magnetic fields that, are exponentially decaying. And they use that as a means of making sure you recognize that Faraday's law is about the rate of change of the flux. So being aware of how it changes isn't enough. You're going to probably have to calculate the derivative, and it can be the derivative of a relatively complex function. So, again, your first job is always to find an expression for the flux. That's where we begin. This one's not too tough. It's always the consideration of 3 variables. Yep.
What power is t raised to on the right? Well, it's kind of.
Oh, I just said t cubed plus b to the t negative 1. I'm just throwing out examples. Like if I was really trying to be careful here, I would have to have some coefficient out front here to make sure it's in Tesla. I didn't do that because the exponential is unitless. But I'm just trying to provide you with this idea that they can give you a complicated function for B. Now, once you get here, again, my expectation is that you will evaluate each variable in succession. Is the magnetic field constant at a snapshot in time?
Yes.
That's an important question to ask. We know the magnetic field in this instance isn't constant over time, but for a specific snapshot, is the magnetic field uniform through the area? That's where the integral comes in. Ask yourself that question. And you're right, the answer is yes. Next, if it's uniform through the area, you don't have to integrate. You just need to know what the area is. In this case, the area, pi r squared. Or A. They might not give you the shape of the wire. They might not say it's a circle. They might not give you anything and just tell you that the area is 4 meters squared. That's all you need. And then, of course, ask yourself, does the angle matter? Is the angle in any way part of this question or not? If it is, put a placeholder. If it's not, put in the constant, whatever it is. I'm putting in 0 degrees, but they could have it at some angle, 45 degrees, 12 degrees, who knows? They're just making sure you are going through and stepping and asking if each of these things are relevant. But overall, that'll be your flux. So now when asked to calculate the EMF, you're trying to place through this a means of figuring out which part of your system is changing. Ask yourself about the number of turns, but also be prepared to have some expression that might deal with the rate of change of the magnetic field or the derivative of the magnetic field with respect to time. Remember dot notation, don't forget about it. Dot notation suggests the first derivative of a variable with respect to time. So if this was the first function, you would have to put the first function in there. If there's a second function, you'd have to put the second function in there. Here's the hard part. Let's, for just a moment, say that it's the first function. Okay? at cubed plus bt to the negative 1. Let me go to another page here. That would mean the EMF is going to equal minus pi r squared times the derivative of at cubed plus bt to the negative 1. Now, this isn't a huge problem. I think most of you can do this with relative ease. We all okay with that? Any question about it? All right. How about this question? What's the direction of the current? The direction of the current has to oppose the change in the magnetic field. In a problem like this, the current is changing in a complicated way. There are intervals where the current is increasing and intervals where the current is decreasing. Perhaps even intervals where the current changes the magnetic field changes direction. You might be required to figure out when the current is traveling in a certain direction based on a function. Because in this case, the function is not obvious. So, case number 2. Be prepared for a complicated magnetic field with respect to time. Kind of remember that when we deal with flux, so far, we've been pretty fortunate in that our calculation for flux has not really required us to consider the vector components of the magnetic field and the area, but it can't stay that way. So having a system where the magnetic field is at an angle relative to your enclosed area is something you're going to have to consider being prepared to do. In this case, I need to remind you that it doesn't matter which way I draw the direction of the area. My vector for area is perpendicular to its surface. So whether I draw it that direction or draw it that direction, I'm still indicating or will have the same answer as a result of this. We're just trying to see how much of my area is in the direction of the magnetic field. And I'm going to get the same value. I might get a negative in here somewhere. But let's just remind ourselves that that negative sign is really just going to be indicative of what the direction of the EMF will be when we get to that point. For right now, that negative sign really doesn't matter. We're focused on the magnitude of our flux. And we get maximum magnitude at 0 degrees and 180 degrees. So just for argument's sake, I'm going to use this as the vector for the area. But this is different than when we did Gauss's law. And I would hope you'd put the emphasis in your notes that when we calculate the flux here, we don't have an enclosed space. So we don't have an automatic direction for the area. In an enclosed space, this is Gauss's law, the direction of the area is outward, away from the enclosure. But for this two-dimensional object, there is no assigned direction because there is no enclosure. So we get to choose that direction. I'm bringing it up because there's not many, a handful of problems that try to exaggerate this or try to play with this idea. But again, any negative sign introduced in the calculation of flux is just going to be related to the direction of the current, which you can get 100% from the right-hand rule without needing to know anything else about the system. I would be remiss if I didn't at least indicate that the angle that we're dealing with is one related to that dotted line. So I'm lining up the dotted line with the direction of the magnetic field, since that's the first vector, and the dot product is between the first vector and the second vector. So it's measured from the first vector to the second vector, making this our angle. So when I calculate the flux, I think I can just write this as B dot A, where A represents the area, times the cosine of whatever that angle happens to be. And I don't need much more than that. If you want, they might give us that this is X units long and this is Y units wide, but that's neither here nor there. It could be any shape. It's just about the area enclosed. Now, I'm being deliberate here because our calculation of flux freezes a moment in time. But our calculation for EMF is about how something changes with respect to time. So we're going to be taking the derivative of that, and we will only have an EMF if something in here changes. And if you haven't figured out where this problem is going, then let me illuminate you. We're going to spin this so that it spins at a spin rate of omega, which means this angle is related to a spin rate of omega, about the pivot point at its middle. You guys in mechanics see how we can work in a lot of mechanics stuff here if we wanted to. They typically shy away from that, but it doesn't mean it's not, part of our problems. It could be. Now, here's the thing I think students tend to miss. The flux is related to theta, but theta is not a constant anymore. In fact, if this has a constant omega, then can you come up with the relationship between theta and omega? Because it might not be given to you on the test. If omega is a constant, then it's quite simple. Theta equals omega times t. It's a motion equation. Remember, theta as a function of time. Now, the reason that's important is that if it's rotating at a constant rate, my flux is going to be BA cosine omega t. Because theta isn't a constant. Theta is constantly changing. So the rate at which it changes should be inserted for theta. So they might just tell you it oscillates at omega. It is up to you to recognize what that does for the cross product. For the dot product. They're not going to give that to you. So in your bold letters there, you need to work in an expression for theta as a function of t if there's some kind of rotational dynamic to your system. I'll say that again in your notes, maybe a box, maybe a highlighter. If you know that there's going to be some angle dependence, you need to find out what the angle dependence is. If it's a constant velocity, it's easy. But my understanding is we have a whole litany of motion equations related to theta. At least one more that I know could play a role. Right? Any of the rotational kinematics equations can play a role here. More importantly, we don't have to be limited by them because we know what causes the rotation in the first place. So there's no reason why they couldn't give us some external torque on the system and we have to come up with an expression for our motion equation. Just remember, this is the big leagues now. The most likely is this, that they're going to say it oscillates at omega. What does that mean for our problem? And that's the most likely. And when I say most likely, there's going to be multiple choice stuff like this. This is probably one of the easiest ones for us to make in the lab too. But getting to another page, that if we spin it faster, these wires are going to be moving faster, and if they're moving faster, there's going to be a stronger force on them. None of that seems crazy, except that think about creating our EMF minus n ddt of B A cosine omega t has to then be passed through our derivative function. So minus n B A, and now we're looking at just the derivative of cosine omega t. Now, this part's not particularly tough. You get another negative sign though. And don't play hard and fast with the rules here. The negative sign still is Lenz's law. Taking the derivative of cosine and getting sine doesn't really change that. Especially with what we're going to get next. When you take the derivative of cosine omega t, you're going to get omega out front first. And then the derivative of your function gives you sine omega t. Well, that's your EMF. But that's a wave function. Luckily, you've had pre-calculus, so you understand how wave functions work. But at minimum, this should conjure up in your mind what this EMF looks like. The fact that it's sine means it starts at the origin, but I don't think that's the important detail. This is EMF as a function of time. And of course, it forms the basis for an alternating potential, which is what we have as the way in which we transmit electricity. There's a lot of stuff in here that's minor that you're probably not seeing that I need to point out to you. The first is that we have a frequency dependence here. For example, the electricity transmitted in this country is transmitted at 60 hertz. So we need to use a word from first semester here, frequency, lowercase f. Omega is angular velocity, but omega is also angular frequency. It's how fast the loop is spinning, but it's also how much it's resetting itself, how often it's getting back to zero. Frequency would be in cycles per second, while omega would be in radians per second. So there is a dependence here between frequency and angular velocity of the loop. This would be measured in hertz, and it's not uncommon for them to say that you have an EMF that has a 60 hertz refresh or a 60 hertz cycle. Again, all the electricity in the room is at 60 hertz. Europe uses 50 hertz. I'm not sure why the difference. Interestingly enough, the other thing I want to point out is there's no omega dependence here. That means you get a bigger EMF if you spin it faster. That doesn't seem too crazy because we know in the spin power, we have a fixed 60 cycle refresh, which means that this number is fixed in all of our electronics. So when we generate electricity, the wall generates 120 volts. That's measured 0 to peak, 240 peak to peak. So when we send electricity into the room, we are sending it in a very specific way. This is not arbitrary. You know omega is a fixed value for our country, so they have to establish everything else just right so that we generate 120 volts peak to peak, send that out. We need to make sure that everybody's electrical system is the same. That's on purpose, so that when you plug something in, the thing you plug in knows what to expect. If you don't do it that way, you'll have problems with the electronics. Anybody who goes overseas knows the plugs don't look the same. It's not accidental, that's purposeful because they don't provide the same thing. A lot of European cities work on a 240 0 to peak electrical system. In some places in our country, it's not 120, it's 110. All of these things have to be taken into account in such a way that when you plug something in, it's going to work. Now, the truth is, everything I'm talking about with electricity here is wrong. That's not how we do it. The final stage converts the power, but there's a transformer located somewhere before the school. And that transformer steps the voltage down to what we see in here. The reason why Tesla was a genius wasn't because of this. It was because he found a way to transmit power with less loss due to resistance in the cables using high voltage transmission systems. You see, one of the most amazing things we're going to learn about Faraday's Law is the ability to transform power from one voltage to another with no loss. That's what those transformers do. You guys have probably been around when a transformer's blown before. It's pretty nasty. A lot of black smoke, power goes out for a couple of hours as they bring a truck out here to put a new transformer out there. They're gonna blow. They blow in the summer all the time because they're hot. There's oil inside them to help cool them, but they get hot, eventually they just blow. Or better yet, lightning strikes them, which is spectacular. Just spectacular, but you don't want to be around it when it happens. So, I think you guys see the bigger picture here. 4 things control this particular voltage. You'll notice I keep ignoring the sine part. Why do I keep ignoring the sine part? If you haven't figured out yet, the sine part's never a constant number. This EMF is repetitive. That's the EMF it produces. So you'll be asked, what is the peak EMF? That's this out front. That's the peak value. But this voltage is never at that value very long. It's always going back and forth between a positive that value and a negative that value, and it cycles based on the sign that's here. We tend to hear about RMS voltages? My assumption is you know what RMS is because you've had, math. How likely is that to be true?
Not at all.
Not at all? Well, that's a disappointment. You've never done RMS?
Never even heard of it.
What are they not teaching you? All right, because RMS is about 0.77 of peak EMF. So I want you to think about this for a little bit. This is hard to come up with all the way, but for just a moment, if I told you that the peak voltage in the room is 120 volts, but we know we're not getting 120 volts all the time. If you calculate the RMS, you find that your actual RMS voltage is about 77% of the peak. That's what RMS does. If you look at just what the RMS value is. I don't ever actually calculate RMS. Nobody does. They just multiply their peak by 0.77, and that gives you the RMS value. What they have found is that in actual work, like the working amount of energy you get is actually about 0.68 of peak. So the RMS provides an adequate, albeit a little overzealous average that closely models or closely fits the actual power delivery of a circuit. Now, none of this conversation is on the exam, but it's important, I think, to understand that RMS is the standard way that we estimate the amount of power delivered by a oscillating voltage. Now,